Welcome. It's late now, and the world has gotten smaller. Just you and the quiet between your breaths, and this voice in the darkness. I'm glad you're here. This is Sleepy Mind Lab, and for the next while, we're going to drift together through some of the strangest truths about reality that we know. Light traveling for billions of years that will never reach us. Time itself coming to an end. Atoms that were forged in the hearts of dead stars now moving through your body. We're going to move slowly. There's no rush, and nothing you need to memorize or prove. Just settle in. Let your mind wander where it wants to go. Because the universe is far weirder than your everyday life suggests. And tonight, we get to sit with that weirdness together. So take a breath. Get comfortable. And let's begin at the very edge of what we can see. The edge of seeing. There is a question that cuts to the heart of everything we know about the cosmos. How far away can something be and still have its light reach us? Seems simple, right? Light travels. It gets here eventually. But here is where reality gets strange. Imagine you are standing at the edge of an ocean, and waves keep pushing you backward. Someone far out in the water tries to swim toward you. They swim as fast as they possibly can. But the current is also pulling them away, and it is getting stronger the farther out they go. At some point, the current wins. They can swim forever and never reach the shore. They are still alive. They are still swimming. But the ocean itself is moving faster than their legs can carry them. This is what is happening across the universe right now. The universe has been expanding for 13.8 billion years. Space itself is stretching. When light travels through stretching space, it still moves at light speed. Yes, 299,792 kilometers every single second. That is the cosmic speed limit. Nothing goes faster. But here is the trick. Space expands faster than light at extreme distances. The universe is not just big and getting bigger. It is expanding faster and faster as time goes on. So light from the most distant galaxies is still in transit right now. Some of it will arrive eventually. But some light will never make it here at all. The gap between those distant objects and us widens faster than photons can close it. They keep traveling toward us, but they lose ground the entire way. The observable universe, the sphere of all galaxies we can possibly see, is not all that exists. It is simply all we can ever know. Everything beyond that edge, forever hidden, forever unreachable. If there is a horizon we cannot see beyond, how do we know there is anything beyond it at all? Light travel delay. Here's something that will change how you see the night sky. Right now, at this exact moment, the sun you perceive is already 8 minutes gone. The light hitting your eyes left the sun's surface 8 minutes ago. You are not seeing the sun as it is. You are seeing a photograph of the sun from 8 minutes in the past. This isn't metaphor. This is how the universe actually works. Light travels at the fastest speed possible, yet even that speed is slow enough that distance becomes time. Think about the nearest star beyond our sun, Proxima Centauri. The light you would see from that star took 4 years and 4 months to reach Earth. You would be looking at a fossil image, a ghost portrait of how that star appeared before you were born, before many people reading these words were born. Now, step further out. The Andromeda Galaxy, the nearest large galaxy to ours, shows you light that departed its stars 2.5 million years ago. When those photons began their journey, your ancestors were learning to chip stone tools. They walked the African savanna. Those photons have been traveling through the vacuum of space ever since, finally arriving at your eyes tonight, carrying an ancient message. This is the strange truth at the heart of astronomy. We do not see the cosmos as it is now. We see it as it was. Every distant object is a time machine showing us the past. Distance and delay are the same thing in an expanding universe where light speed has a limit, and that limit means we are always looking backward. Galaxies in retreat. Here's something that would have seemed impossible a century ago. In the 1920s, an astronomer named Edwin Hubble pointed his telescope at distant galaxies and made a discovery that changed everything. Nearly every single galaxy he looked at was moving away from us. Not just one or two, almost all of them. The entire universe seemed to be running away. But here's the really strange part. The farther away a galaxy is, the faster it moves away. A galaxy twice as distant rushes away twice as fast. A galaxy 10 times farther speeds away 10 times quicker. This pattern is so consistent that scientists call it Hubble's law. Now, your first thought might be that we're somehow special, that galaxies are fleeing Earth specifically. But that's not what's happening. Imagine painting dots on the surface of a balloon. As you blow air into the balloon, the rubber stretches everywhere at once. All the dots move apart from each other. The dots that were farthest away seem to move fastest, not because they have rockets pushing them, but because there's more rubber, more space, being created between them and everything else. That's what's happening to galaxies. Space itself is expanding, carrying galaxies along with it like passengers on an invisible current. The universe isn't flying apart. The universe is stretching. And the deeper you look into the cosmos, the more you realize that everything we see is slowly, constantly, drifting away from everything else. The question is why? The red shift. Imagine standing on a platform as a train pulls away. The whistle starts high-pitched as it approaches, then drops lower as it recedes. You've experienced this your whole life. It's called the Doppler effect, and light does exactly the same thing. When a galaxy rushes toward us, its light waves compress. They bunch up tightly, shifting toward the blue end of the spectrum, toward shorter wavelengths. But almost every galaxy we observe is moving away from us. And when something moves away, its light stretches. The waves spread out. They shift toward red, toward longer wavelengths. This is the redshift. Now, here's where it gets powerful. Every element in the universe has a unique fingerprint. Hydrogen leaves a distinctive mark in light, as does iron, as does carbon. Astronomers know exactly where these fingerprints should appear in the spectrum. But when they observe distant galaxies, these fingerprints have slid toward the red. The further they've slid, the faster that galaxy is running away from us. It's like reading a cosmic speedometer written in light itself. The redshift tells us velocity, and velocity tells us distance. And distance, remember, is time. We're looking back toward the universe's infancy. The universe is writing its own history in the stretching of its light. Cosmic acceleration. So we know the universe is expanding. Galaxies are rushing away from each other across billions of light years. You might think gravity, that cosmic pull that holds planets to stars and moons to planets, would slow that expansion down over time. The whole universe pushing outward should gradually lose speed, like a ball thrown upward against Earth's gravity, slowing as it rises. But in 1998, astronomers studying distant supernova stellar explosions billions of light years away discovered something that shouldn't be true. The expansion wasn't slowing. It was accelerating, getting faster. The galaxies aren't just moving apart. They're speeding up their retreat. This was genuinely unsettling. Something is pushing the universe apart harder and harder every moment. We call it dark energy. But here's the honest truth. That name is just a label for something we don't understand. We detect its effects, we measure its strength, but we have no idea what it actually is. Dark energy makes up 68% of everything, 68% of all the mass and energy in the entire universe, and we're essentially clueless about it. It's as if space-time itself, the fabric that holds space and time together, has an inherent property that pushes outward. Negative pressure. A cosmic repulsion baked into reality at the deepest level. Imagine filling a balloon with air, but the air itself wants to expand faster and faster. That's closer to what we're describing. Except instead of a balloon, it's the whole cosmos. Instead of air, it's something we can't touch or see or fully comprehend. If this acceleration continues forever, if dark energy keeps winning against gravity's pull, then the far future of the universe takes on a strange and lonely shape. Galaxies will drift beyond each other's horizons. Stars will burn out. The darkness will deepen in ways you might not expect. But we'll explore that later. Galaxies beyond our reach. There are galaxies out there right now whose light is racing toward us at 186,000 miles per second. Maximum speed, nothing faster. Yet these galaxies are moving away from us so quickly that the distance between us keeps growing. The light chases. The space expands faster. The gap widens instead of closes. Imagine running towards someone on a moving walkway that moves backward faster than you can run forward. You never get closer. You only fall further behind. This is not metaphor. This is happening across billions of light years. And here is where it becomes strange. That light will never reach us. Ever, no matter how long we wait. No matter if we exist for another trillion years. But there is more. As space stretches and stretches, it pulls that light with it. The waves get longer. Longer. The light shifts from visible to infrared to microwave to radio. The energy drops, drops, drops. Eventually the photon becomes so stretched, so cold, so red-shifted that it arrives carrying almost nothing. A whisper instead of a song. There is a hard edge to what we can ever know. A boundary we cannot cross. Beyond that line sit galaxies full of stars and planets and perhaps life, and we will never see them. They might shine brilliantly in their own sky, but to us, they are already gone, already invisible, already impossible. The universe is not infinite to us. It is finite, and we live at the center of our own prison of light. Deep time. Think about your own life for a moment. You've been alive maybe 15, 20, 50 years. That feels like a long time, doesn't it? Your childhood seems distant. A decade ago feels like ancient history. Now zoom out. Human civilization as we know it goes back about 5,000 years. That's where writing began, where we started recording ourselves. 5,000 years sounds enormous, until you realize it's barely a blink in deep time. Zoom out further. Life on Earth has been evolving for about 4 billion years. Dinosaurs walked this planet for 160 million years before they vanished. Humans have been here for only 300,000 years. We arrived so late that we missed almost the entire story. But here's where it gets truly strange. The Earth itself is 4.5 billion years old. The rocks beneath you are older than you can imagine. And yet the universe is nearly 3 times older than that. 13.8 billion years. That's how long light has been traveling through space since the beginning. When you look at the most distant galaxies through a telescope, you're seeing light that's been journeying since before our sun existed. You're looking backward in time, watching the universe as it was when it was young and hot and impossibly dense. All of that time compressed into the universe's first fraction of a second came from something impossibly small, something smaller than an atom. Everything that ever was, burning at temperatures beyond comprehension. The universe has been expanding and cooling ever since. And if the universe had a beginning so violent and strange, what about its end? The Big Bang. Here's something that would have seemed absurd 100 years ago. In 1916, Albert Einstein published equations that described how space and time behave. Most physicists looked at those equations and saw something static, a universe that had always existed, unchanging, eternal. But the math was whispering something else entirely. The equations suggested space could do something wild. It could expand, it could contract, it could move. Then, in 1929, an astronomer named Edwin Hubble pointed his telescope at distant galaxies and made a discovery that changed everything. Those galaxies weren't sitting still. They were moving away from us. And the farther away they were, the faster they were retreating. Imagine throwing a ball into the air and watching it fall slower and slower as it climbs higher. That's what the universe was doing, but in reverse. Galaxies rushing outward, space itself stretching. Now comes the strange part. If space is expanding right now, that means if you rewind time, if you play the universe backward like a film in reverse, space must get smaller, denser, hotter. Squeeze it back far enough and something extraordinary happens. Everything collapses into a single point. A place where all matter, all energy, all space, all time were compressed into infinite density. A singularity. This moment, this beginning, we call the Big Bang. But here's the crucial thing to sit with. It wasn't an explosion that happened inside space. It was an explosion of space itself. The birth of time itself. Everything that would ever exist emerged from that moment. And that moment came from nowhere we can currently see. Cosmic microwave background. Right now, at this very moment, invisible light from the beginning of time is passing through your body. You cannot see it or feel it, but it is everywhere. Every direction you look in the night sky, ancient photons are arriving particles of light so old they were born before any star, before any galaxy, before the universe even cooled down enough for atoms to form. This is the cosmic microwave background, and it is the oldest light that will ever touch Earth. Here is what happened. In the very first moments after the Big Bang, the universe was impossibly dense and hot, filled with a thick soup of energy so intense that light could not travel freely. Photons would get absorbed and re-emitted constantly, bouncing around in the chaos. But as the universe expanded, it cooled. And 380,000 years after the beginning, something extraordinary occurred. Electrons and protons finally had enough room and low enough energy to combine into neutral atoms. Hydrogen formed, and in that instant, light was freed. For the first time, photons could stream across space without being trapped. That released light is what we detect today. But the universe has spent the last 13.8 billion years stretching. Every photon has been stretched and cooled by the expansion of space itself. What was once visible light has become microwave radiation visible to your eyes, but bright and clear to radio telescopes. When we measure this ancient glow with precision, it matches our predictions perfectly. And embedded in the tiny patterns of its temperature are clues about how our universe was born. What do those patterns reveal about the cosmos's deepest secrets? Temperature of creation. Let me ask you something. How hot can you imagine? The surface of the sun feels like nothing compared to what I'm about to describe. Think about the core of our sun. That's about 27 million Kelvin. Imagine standing there. You'd be vaporized instantly. But that's actually cool compared to the first fraction of a second after the Big Bang began. In those opening moments, the universe was so intensely hot that matter itself could not exist. Not rocks, not atoms, nothing solid. Just pure energy screaming everywhere in all directions. We're talking 10 billion Kelvin or higher, maybe much higher. At that temperature, something wild happens. Particles and their opposites, antiparticles, were constantly flashing into existence and immediately annihilating each other in little explosions. It was like the universe was a cosmic furnace where matter and antimatter were dancing in and out of being thousands of times per second. And here's the really strange part. At that extreme heat, all four of the universe's fundamental forces were merged together. Gravity, electromagnetism, the weak nuclear force, the strong nuclear force. They weren't separate. They were unified. One single cosmic fire. But then, something began to happen. The universe expanded, and as it expanded, it cooled. It's like pulling apart a compressed flame and watching it dim. As the temperature dropped, symmetries broke. Forces separated. Quarks could finally stick together and form heavier particles. Then atoms formed. Then molecules, galaxies, stars, and eventually you. All of phase everything you are came from that cooling. Everything emerged from heat becoming cold. Isn't that strange to hold in your mind? Time has a direction. Here is something you've always known but never quite thought about. Drop a glass on the floor. It shatters into jagged pieces. Those pieces will never, on their own, leap back together and reform the glass. An egg cracks into a bowl. You scramble it. The molecules jumble and mix. That scrambled egg will never untangle itself back into a whole, uncooked egg. This is not a law of physics telling you it is impossible. It is something deeper. It is about probability. When you shuffle a deck of cards, you make it messy, random. The chances that shuffling will create perfect order, all hearts together, then diamonds, then clubs, then spades, are so tiny, they might as well be zero. It is not impossible. It is just so incredibly unlikely that it will never happen. The universe works the same way. There are vastly more ways for things to be disorganized than organized. Entropy is the name physicists gave to this disorder. It measures how many possible arrangements atoms can have. And here is the strange part. Entropy always increases. Always. Hot coffee left on a table does not get hotter. It cools down, spreading its heat into the air around it. Heat flows from hot to cold, never backward on its own. Why? Because there are more ways for energy to be spread out and disordered than concentrated and hot. This increase in entropy, this spreading of disorder, is what gives time an arrow. It points forward. You remember yesterday. You cannot remember tomorrow. Your body ages and decays. The universe expands and dissipates. All because disorder is more likely than order. The second law of thermodynamics turned this simple truth into the reason time feels like it flows in one direction. But if entropy always increases, always spreads disorder further, what is the ultimate destiny of everything? Heat death. Don't imagine the end of time as a bang or a crash. Imagine a slow fade, a dimming, a quiet. In a quadrillion years, that's one followed by 15 zeros. The last stars will go dark. The biggest ones burned out billions of years ago. The smallest, those dim red dwellers, they lasted longest. But even they run out of fuel. When that final star collapses into ash, the universe will have only starlight's ghost to live on. In 10 to the 15th years, entire galaxies will have decayed into scattered remnants. Not exploded, decayed. Like a log rotting in a forest, except the forest is everything and the rot takes longer than any human mind can hold. Billions of years after that, something stranger happens. The protons themselves, solid centers of atoms, the things you're made of, begin to break apart. We're not even sure this happens. Physics suggests it might. In that scenario, in 10 to the 25th to 10 to the 50th years, all matter crumbles into radiation. Electrons and positrons and photons scattered so far apart, they will never touch again. What's left is a thin, cold soup. Not liquid. Not gas. Just particles. Lone photons traveling through endless dark. Neutrinos that have crossed the universe 1 trillion times without hitting a single thing. The temperature drops below 1 degree Kelvin, then below 1/1000th of a degree. The universe becomes a nearly perfect vacuum, and what little energy remains is spread so evenly that no two things are different enough to do any work. This is heat death, not burning, freezing, not active chaos. Perfect cold balance. No reactions. No change. No time in any meaningful sense, because nothing moves or shifts or becomes. In that state, could anything still think? Could anyone remember? Could anything care that once, briefly, minds like yours lit up and wondered about all this? The age of stars. Think about our sun for a moment. It has been burning steadily for about 4.6 billion years, and it will keep burning, keep fusing hydrogen into helium in its core, for another 5 billion years or so. 5 billion years. That is longer than all of life on Earth has existed. Longer than dinosaurs walked here. Longer than humans have been around by a factor of thousands. But here is where it gets strange. When our sun finally exhausts its fuel and swells into a red giant, engulfing Mercury and Venus and scorching this planet to ash, the universe will still be young. Almost impossibly young. Because after that star dies, the universe will continue burning other stars for trillions of years. 1 trillion is 1,000 billion. The age of stars as a whole will last about 100 trillion years. That is 10 to the power of 14 years. Now hold that number. 100 trillion years. The entire lifetime of every star in every galaxy, all burning out one by one, is just the opening chapter. After that, when the last star gutters out and dies, when there are no more suns anywhere in existence, the universe will still have 10 to the 100th years remaining. A number so enormous that if you wrote out every single zero, it would fill this room, every building you have ever been in, entire cities, entire continents. Stars are not eternal. They are candles. And we live in the first moment of infinite night. Dark matter. Imagine you're watching a cosmic merry-go-round. Galaxies spin. Stars orbit their centers, held in place by gravity. But here's where it gets strange. When astronomers measure how fast these stars move and calculate the gravity needed to keep them from flying apart, the numbers don't add up. The visible matter, all the stars you see, all the gas clouds glowing in telescopes should only provide about 1/5 of the gravitational pull required. Yet the galaxies hold together perfectly. They don't tear apart. This was discovered in the 1970s, and it meant something radical had to be true. There had to be 5 times more matter than we could actually see. Invisible matter. We call it dark matter, and it comprises about 27% of everything in the universe. Think of it like this. You're at a concert. You hear music filling the room, but you can't see the speakers. The sound is real. The source is real. You simply can't perceive it with your eyes. Dark matter is the universe's hidden speaker. It doesn't emit light. It doesn't absorb light. It only pulls, only gravitates. Galaxies are like islands of light, floating in an ocean of invisible substance. The dark matter forms a scaffolding around them, a gravitational web that holds galaxies in their places, guides their movements, shapes the cosmic structure itself. We don't know what dark matter actually is. Not antimatter, perhaps exotic particles that barely interact with ordinary matter at all. They're called WIMPs. They pass through you constantly, right now. And if 85% of all matter in the universe is invisible, what else are we blind to? Dark energy. Here's a thought that might keep you awake. We've talked about how the universe is accelerating its expansion. We know this happens. We've measured it. But now comes the stranger part. We don't actually know what's doing the pushing. Dark matter is invisible, sure, but it's still matter. It has mass. It pulls things toward it through gravity, just like normal matter does. You can understand that. Dark energy is different. It's something else entirely. Dark energy appears to be a property of space itself. Not something in space, but something about space. And here's the unsettling part. It doesn't pull, it pushes. The more space there is, the more dark energy there is. And the more dark energy there is, the harder it pushes space apart. Think of it like this. Imagine space is a balloon. But instead of you blowing air into it, the balloon itself is creating more air the bigger it gets. And that new air pushes the balloon's surface even faster. The expansion feeds the force that causes more expansion. It's self-accelerating. It builds on itself. We have no idea what dark energy actually is. Is it a quantum field we haven't discovered yet? A property of the vacuum itself? Something we haven't even imagined? We cannot touch it. We cannot see it. We can only detect it by watching how it bends the universe around us. And yet dark energy makes up 68% of everything. It is the universe's dominant force. And we're essentially blind to it. So what do you think about that tonight? A force that makes up most of reality, and we're left completely in the dark. The invisible cosmos. Here is something strange to sit with. Everything you have ever touched, every person you have loved, every star you have ever seen in the night sky, every galaxy we have pointed our telescopes at, every atom in your body right now, all of it together makes up only 5% of the universe. 5%. That means 95% of everything that exists is completely invisible to us. We cannot see it. We cannot touch it. We have never directly detected it with any instrument we have built. And yet, we know it is there because we can feel it. We can measure its weight. We can watch it bend light and bend space itself. Imagine living in a city where 95% of the buildings are made of a material you simply cannot perceive. You cannot see them. You cannot photograph them. You walk through them every day and feel their gravity pulling on you. You see the effects of doors opening and closing on their own. You watch clouds of dust swirl around them. You measure their mass and their motion. But the buildings themselves remain forever hidden. That is our cosmos. We are living in a universe that is almost entirely made of things we cannot see. Dark matter pulls at galaxies with an invisible hand. Dark energy pushes everything apart with a force we do not understand. And here we are, tiny, visible, made of atoms that clump together in this rare, thin, luminous way. We are the unusual 5%, islands of fire and structure floating in an ocean of darkness. The question that lingers now is simple. What is the 95% made of? And what does it mean that we are so thoroughly outnumbered by the invisible? Black holes. Imagine compressing the entire Earth Hall. 6 sextillion tons of itinto, a sphere the size of a marble. The gravity of that surface would be so intense it would flatten atoms into paste. Now compress it down to the size of a grain of sand. The gravity intensifies exponentially. Keep squeezing. Keep squeezing. Eventually, you reach a point where the density becomes infinite, where all that mass collapses to a single point of infinite heaviness. That is a black hole. Here is what happens. A star dies and its core collapses. If that core is heavy enough, gravity overwhelms every force that tries to push back. The mass crushes inward past a critical boundary called the Schwarzschild radius. For a star as heavy as our Sun, that radius is about 3 kilometers across. Once you cross that invisible line, you enter the event horizon. And the event horizon is where escape becomes impossible. You could launch a rocket at light speed and still never leave. Not because the rocket is too weak, but because the very fabric of space is curved so sharply that all directions point inward. Every path leads toward the center, toward the singularity. Gravity becomes stronger than any force in physics. Not even light survives. Light falls in and never comes out. That is why they are black. But here is the true strangeness. What happens to time itself as you cross that point of no return? Event horizons. Imagine you're standing safely far from a black hole, watching a friend in a spacecraft slowly approach its edge. What happens next is so strange that it bends your mind in half. Your friend pilots closer and closer, and you're watching them on a monitor. But something bizarre occurs. As they near the boundary, their movements begin to slow down. Not because they're being cautious. The universe itself is doing something to time. Their clock, visible on your screen, ticks slower and slower. They wave at you, but the wave stretches out in time. It becomes sluggish, ghostly. Their image reddens as light itself gets pulled downward by gravity, and then they seem to stop, frozen at the moment of crossing, locked in time, never quite reaching the edge. From your perspective, it looks like they're suspended forever at that boundary. But here's where it gets even stranger. Your friend experiences something completely different. Inside their ship, their watch ticks normally. Their heartbeat is steady. Time feels the same as it always does. They cross that boundary event horizon without noticing anything catastrophic happening at that instant. No war, no impact. Just a smooth passage inward. Nothing catches them, not yet. The real horror comes later, deep inside, where gravity stretches different parts of their body at different rates. We call this spaghettification. The pull on their feet becomes vastly stronger than the pull on their head. They get torn apart slowly, but that's not the boundary. The event horizon itself is stranger still. It's not made of anything. It's not a thing at all. It's a line beyond which cause and effect break. Information that falls in cannot climb back out. Signals cannot escape. The universe outside and the universe inside become completely disconnected. Two realities separated by mathematics. Time near a black hole. Here's something Einstein figured out that changed everything we thought we knew about time. Time is not the same everywhere. It moves at different speeds depending on where you are and how much gravity is pushing down on you. Think about it this way. Gravity doesn't pull things toward it. Instead, massive objects bend the fabric of space and time itself around them. The stronger the gravity, the more extreme that bending. And here's where it gets strange. That bending actually slows time down. We're not talking theory here. Scientists have taken atomic clocks, the most precise instruments we have, and placed them on airplanes, flying high in the sky. Then they compared those clocks to identical ones sitting on the ground. The clock in the plane, experiencing less gravity, ticked slightly faster. We measured it. Time really does move at different rates. Now imagine standing at the event horizon of a black hole. The gravity there is so incredibly intense that time slows to a crawl. To an outside observer watching from a distance, you would appear to freeze. Your clock would appear to tick slower and slower and slower until it seemed to stop completely. From your perspective, time feels normal. But to someone far away, you're essentially frozen in place, trapped in a moment that never quite finishes. Time doesn't just bend near a black hole. It approaches something that looks like a standstill. This isn't poetry or metaphor. This is what happens when you encounter gravity so extreme that it warps the very fabric of time around you. What does it mean when time can actually stop? What are you really experiencing if you're moving through frozen moments? Singularities. Here is where physics goes silent. At the very heart of a black hole, at the center where the event horizon surrounds everything, lies something we have never seen and may never understand. A singularity. And here is the honest truth we must sit with. We do not actually know what happens there. General relativity, Einstein's theory of gravity, makes a clear prediction. It says that all the mass of a collapsed star gets crushed into a single point. Infinite density, zero volume. Imagine trying to pack the entire mass of Earth into a grain of sand, then pack that grain into something 1,000,000,000,000 times smaller, then smaller still. Keep going forever. That is what the mathematics says should happen. But here is where things get strange. In physics, when your equations predict infinity, that is usually a red flag. It means your theory has hit a wall. It means you have pushed the math beyond where it actually describes reality. And that is exactly what happens at a singularity. Two of our best theories, the ones that explain everything we know, completely contradict each other there. General relativity says one thing, quantum mechanics says another. Neither one works. Both of them fail. We suspect the truth is something else entirely. Maybe quantum effects prevent true singularities from forming at all. Maybe there is quantum fuzz instead. Maybe there is a bounce. Maybe even a tunnel to somewhere else. But we cannot look inside to check. The singularity hides forever behind the event horizon, untouchable, unknowable. What really lies there remains the deepest mystery in physics. Hawking radiation. Here's something that might seem impossible. Black holes are not completely black. They leak, they radiate, and eventually they die. In 1974, a young physicist named Stephen Hawking did the math and discovered something that still bothers physicists today. At the edge of a black hole, right at the boundary called the event horizon, the universe behaves in a way that seems to violate everything we think we know about black holes, being traps from which nothing escapes. Imagine the quantum vacuum as a seething foam. At the tiniest scales, particle pairs are constantly being born from nothing. An electron and its opposite, a positron, flash into existence for an instant and then annihilate each other, cancelling out. This happens everywhere, all the time. Usually, you'd never notice. But at the event horizon of a black hole, something strange happens. A virtual pair appears right at that boundary. One particle gets pulled past the horizon into the black hole. The other escapes outward into space. The particle that escaped carries away real energy. The black hole, having lost that energy, becomes slightly less massive, slightly smaller, and so it radiates. This seems wrong somehow, a black hole losing mass, but the math is clear. The smaller the black hole, the hotter the radiation, the faster it evaporates. A stellar mass black hole would take longer than the current age of the universe to evaporate, but a black hole the size of a mountain would release its entire remaining mass in an explosion brighter than 1 billion suns. The supermassive black holes at the centers of galaxies are so enormous that their evaporation would take 10 to the power of 67 years. That number is so vast it makes the age of the universe look like a single second. But here is the strange part. Eventually, every black hole in existence will evaporate. Every one. And when it does, all the information it swallowed returns to the universe as radiation. Nothing is truly lost, just changed, just hidden until the very end. Gravity warps space. Imagine space-time as a stretchy rubber sheet, smooth and flat when nothing sits on it. Now place a marble on it, something heavy. The marble sinks down, creating a dent, a curve in the surface. Place another marble nearby. It doesn't roll toward the first one because some invisible force reaches across the space between them, pulling it. No. It simply rolls down the curve of the sheet itself, following the slope created by the dent. This is gravity, not a force reaching through empty space like a tractor beam. A curve in the fabric of reality itself. Einstein showed us that mass and energy don't just sit in space. They reshape space. A star warps the space-time around itself the way a bowling ball deforms a trampoline. Everything nearby, planets, asteroids, even light, follows the curves created by that warping. The Earth isn't being yanked by an invisible rope. It's traveling along the curved path that space-time provides, like a marble rolling down a hill. We call this curved path a geodesic. The straightest line an object can take through warped space-time. Here's where it gets stranger. Light, which has no mass, still follows these curves. A beam of starlight bends around a massive object, deflected by the geometry of space itself. Gravity acts like an invisible lens, focusing and bending light the way glass does. So what we call gravity isn't a force pulling at all. It's the geometry of reality responding to mass and energy. The universe isn't pulling on things. It's curving beneath them. Gravitational waves. Imagine you're standing at the edge of a still pond on a perfectly calm night. The water is glass. Now drop a pebble. Ripples spread outward in all directions, carrying the energy of that small collision across the surface. Most waves we know work like that, but space-time itself can ripple too, and when it does, the universe is trying to tell us something about violence happening somewhere far away. In 2015, scientists detected something they had spent 50 years hunting for: gravitational waves. Real, measured. These weren't waves made of water or light or sound. These were waves made of space-time itself. Here's what happened. 130 billion light-years away, two black holes were spiraling toward each other. They were massive objects, each dozens of times heavier than our Sun, locked in a deadly dance. As they accelerated toward collision, they didn't just move through space. They warped the very fabric of space and time around them. That disturbance, that ripple, spread outward at light speed, like a shockwave through the fabric of reality itself. When those ripples reached Earth, they stretched space-time by less than 1 part in 10 septillion, smaller than a proton's width. Our planet got nudged, ever so slightly, and incredibly sensitive instruments called LIGO could feel it. This matters because for the first time, we had a second way of seeing the universe. Not through light, through the cosmic shudders of violence itself. Gravity now became our new sense. And through that sense, we were about to hear cosmic screams we'd never heard before. Quantum uncertainty. There's a game physicists used to play. They would try to measure an electron. Seems simple, right? Just look at it. But here's where it gets strange. To see something, you need light. You need a photon to bounce off that electron and travel to your eye or detector. But a photon is not gentle. It carries energy and momentum. The instant it hits the electron, it pushes it. The electron moves. So now you know where it was, but you've changed where it's going. This creates a trap. You want to know both things at once: where the electron is right now, and how fast it's moving. Position and momentum. Simple enough, but nature doesn't work that way. If you use a very energetic photon with a short wavelength, you can pinpoint the electron's location precisely. You see exactly where it sits. But that photon carries a lot of momentum, so it hits hard and sends the electron flying. Now you have perfect position, but scrambled momentum. If you use a gentle, low-energy photon with a long wavelength, it won't disturb the electron much. Its momentum barely changes. But a long wavelength is fuzzy. It's like trying to see something through thick fog. You know roughly how fast it's moving, but you have no idea exactly where it is. You cannot escape this trade-off. It's not because our instruments are clumsy. It's not because we haven't invented better tools yet. This is woven into reality itself. Heisenberg discovered that at the quantum scale, nature assigns no particle a definite position and momentum simultaneously. Not because we can't measure both, because both don't exist at the same time. This means reality at the smallest scales is fuzzy, uncertain. A particle exists in a cloud of possibility until you look, which raises a question that will haunt us. If particles don't have definite properties until measured, does the act of measuring create the reality we observe? Virtual particles. Here is something that will shift how you think about empty space. Quantum mechanics says nothing is ever truly empty, not even the void. Imagine a perfectly dark room. You'd think it contains nothing. But at the quantum level, that room is a cauldron. Particle-antiparticle pairs are constantly flickering into existence and vanishing again. An electron and its mirror opposite, a positron, appear for an impossibly brief moment, then annihilate each other completely. This happens everywhere, right now. In the space between you and this voice. In the space between atoms. In the space inside atoms. Why is this allowed? Because of something called the uncertainty principle. It says energy and time are linked. The shorter the timescale, the more energy can fluctuate wildly. For a trillionth of a second, the universe borrows energy from nothing itself and creates particles from that borrowed energy. These virtual particles cannot be seen directly. They exist too briefly, but they leave fingerprints. They slightly alter the mass of real particles. They cause light to scatter in subtle ways. They create a measurable force called the Casimir effect, where two metal plates pushed close together feel an invisible pressure pushing them together. So the quantum vacuum is not empty. It is seething, a boiling sea of ghostly somethings that emerge from nothing, shimmer for an instant, and dissolve back into nothing again. This raises a strange question. If empty space contains all these fleeting particles, what is the difference between nothing and something? Empty space has energy. Here's a strange question to sit with tonight. Can you create absolute nothing? Take a room, remove every atom, every molecule of air, pump it all out, keep going. Remove all light, all heat radiation, everything you can touch or measure. Eventually you're left with what looks like pure emptiness. But here's where it gets weird. Quantum mechanics says you cannot actually reach zero. You cannot have true nothingness. Even in that perfect vacuum, something is there. It's called zero-point energy, and it's woven into the fabric of space itself. Think of it this way. Space isn't like an empty theater after everyone leaves. Space is more like a sleeping animal. Even when it's at rest, it's breathing. At the quantum level, invisible fields permeate everything. These fields are never truly still. They vibrate at their lowest possible frequency, the absolute minimum allowed by the rules of physics. That baseline vibration, that's zero-point energy. It's everywhere. It fills the space between atoms. It fills the space between galaxies. It fills the space between you and everything you see. Scientists can measure its effects. It causes electrons to shimmer slightly in their orbits. It influences how atoms bond. And here's the profound part. Many physicists believe this quantum vacuum energy might be dark energy itself, the mysterious force pushing the universe apart and accelerating its expansion. If they're right, then the empty space between galaxies is not passive. It's active. It's pushing. It's alive in its own strange way. The nothing isn't nothing. It has weight. It has power. It holds the secret to why the universe is expanding faster and faster. What does it mean to live in a cosmos where even absolute emptiness contains hidden energy? Wave-particle duality. Here is something that should trouble you in the best possible way. Imagine you have a flashlight and a wall with two holes cut into it. Shine the light through, and it spreads out like a wave. The light passes through both holes at once, and the waves interfere with each other on the far side, creating a pattern of bright and dark stripes. Now imagine you set up a camera to catch the light red-handed. You want to see which hole it actually goes through. The moment you do this, something strange happens. The light gives up its wave nature. It acts like a particle. It goes through one hole or the other, not both. The stripes vanish. This is not a measurement problem. This is not about our ignorance. This is how the universe actually works. Electrons do the same thing. They behave as waves or particles depending on what question you ask them. Without observation, an electron explores all possible paths at once, like a wave spreading everywhere. The moment you try to pin it down, it snaps into a single location, like a particle. The universe does not commit to a description until you force it to choose. Reality is not sitting there waiting to be discovered. It is context-dependent. It is relational. What something is depends on how you look at it. And that changes everything about what reality fundamentally is. The observer effect. There is a simple experiment that breaks everything you think you know about how reality works. It is called the double-slit experiment, and it has confused physicists for nearly 100 years. Imagine you are in a dark room, and you have a wall with two narrow slits cut into it. Behind that wall is a detector screen. Now you fire electrons at the wall, one at a time. The electrons pass through the slits and hit the screen behind. Here is where it gets strange. When you are not looking, when you are not measuring which slit each electron goes through, something impossible happens. The electron goes through both slits at the same time. Both slits. Simultaneously. And because it goes through both, it interferes with itself like a wave. You see a pattern on the detector screen that only makes sense if the electron was in two places at once. But the moment you set up a detector to watch which slit the electron actually uses, everything changes. You place your measuring device there. You ask the universe a question. Which slit did you go through? And the universe answers. The electron goes through one slit or the other. No longer both. No longer both. No longer interfering with itself. The pattern on the screen vanishes. You get something different entirely. Your observation changed the result. This is not because your measuring device knocked the electron around, disturbed it somehow. Physicists have tested this 100 ways. The disturbance explanation does not hold up. Something deeper is happening. Before you measure, the electron exists in superposition. All possibilities at once. The moment you measure, the moment you force nature to give you an answer, the superposition collapses. One reality crystallizes out of infinite possibility. You are not separate from nature watching it from outside. You are entangled with it. The act of asking a question changes the answer. Observation creates reality, which makes you wonder. If this is true at the quantum scale, what does it mean for all the things we think we observe? Entanglement. Imagine you have two particles born from the same event, the same moment of creation. They fly apart. One heads toward the edge of the observable universe. The other stays in your laboratory. They are entangled. This means their quantum states are locked together in a way that has no explanation in our everyday experience of how the world works. You measure the spin of the particle in your lab. You find it spinning up. In that instant, the other particle across the galaxy has its spin determined as down. Not because a signal traveled between them, not because they were secretly programmed with matching instructions before they separated. Something else is happening. Einstein hated this. He called it spooky action at a distance. It offended his deepest sense of how reality should work. Things should only be influenced by what is right next to them. Distant events should not reach across the void and instantly affect each other. And yet, thousands of experiments have confirmed this is exactly what happens. The weird part is that entanglement does not violate relativity. No information travels faster than light between those particles. But it reveals something profound about reality. The universe is not local. Things are connected in ways our intuition struggles to grasp. Particles separated by galaxies remain part of a single quantum system. They are not independent. They are aspects of one unified whole. This is not magic. It is not sending messages. It is something stranger. Reality, at its deepest level, is woven together in ways that make distance almost irrelevant. Two particles born together remain somehow one, no matter how far they drift. Antimatter. Here's something that should make you pause. For every particle of matter in your body, there exists a ghost twin made of antimatter. An electron has a positron. A proton has an antiproton. They're identical in almost every way except one critical detail. Their charge runs backward. Where an electron carries a negative charge, its antimatter double carries a positive one. Same mass, opposite polarity, like a photograph in reverse. And when they meet, something extraordinary happens. Both particles simply cease to exist. They don't collide and bounce apart. They don't splinter into smaller pieces. Instead, they annihilate completely, converting their entire mass into pure energy. All of it. 100%. A flash of radiation released, according to Einstein's equation. E equals mc squared. To give you scale, 1 gram of antimatter meeting 1 gram of ordinary matter would unleash energy equivalent to a small nuclear bomb. Instant erasure. Nothing left but light. Now here's where the mystery deepens. When the Big Bang occurred roughly 13.8 billion years ago, the laws of physics predict it should have created matter and antimatter in perfectly equal amounts. Two sides of the same coin. They should have encountered each other almost immediately in that early inferno, annihilating completely, leaving behind nothing except radiation. No atoms, no stars, no galaxies, no you. Yet here you sit, made entirely of matter. Billions of galaxies surround you, all matter. We find virtually no antimatter anywhere in the observable universe. It vanished. Or perhaps it never existed in equal quantity at all. This asymmetry haunts physics. It remains one of the deepest unsolved puzzles. Somewhere in the first moments of creation, something tipped the balance. Something chose matter over antimatter. And because of that invisible choice, you exist. Neutrinos. Right now, as you sit here listening, About 100 trillion neutrinos are passing straight through your body. Not around it, through it, through your head, through your head, through your heart, through every cell. And you feel absolutely nothing. Neutrinos are the universe's most elusive messengers. They are particles so ghostly that they barely interact with matter at all. A single neutrino could travel through a light year of solid lead, solid rock, solid anything, and never collide with a single atom. Just drift right through like it was empty space. They come from everywhere. Deep in the sun's core, where hydrogen fuses into helium, neutrinos are born by the trillions every second. They escape the sun's interior and stream toward Earth. They come from supernovae, from the explosive deaths of distant stars. They even come from radioactive decay happening in the ground beneath your feet. For a long time, we couldn't prove they existed at all. Scientists predicted them in 1930, but it took until 1956 to actually detect one. 26 years. Because catching a neutrino is like trying to hear a whisper in a hurricane. Yet these ghostly particles carry stories. They bring information about the sun we can't see any other way. When a star explodes as a supernova, the neutrinos arrive before the light does. Before the visible explosion reaches us, the neutrinos are already here, telling us something happened. We are constantly bathed in messages from the cosmos. We just can't feel them. And that raises a question. What else passes through us that we don't know about? Cosmic rays. Right now, in this moment, you're being struck by cosmic rays. Thousands of them. Every single second, high-energy particles from the depths of space are crashing into Earth's upper atmosphere. They come from supernovae, from the violent hearts of distant galaxies, from sources we still don't fully understand. And they're hitting you constantly. Here's what happens when one arrives. A cosmic ray, usually a proton, sometimes something heavier, smashes into a nitrogen or oxygen molecule miles above your head. The collision is so violent, so energetic, that it shatters the atom and creates a cascade of secondary particles. Pions appear and decay almost instantly into muons. These muons are heavier cousins of electrons, and they're traveling at nearly the speed of light. They slip through the atmosphere, through clouds, through buildings, through your body, and most of them just keep going. Down into the ground, through you. At sea level, you're struck by thousands of these muons every minute. They pass straight through. Your cells barely notice, but that constant bombardment adds up over a lifetime. A small source of radiation that's simply part of being alive on this planet. But here's where it gets strange. The highest energy cosmic rays we've detected, the rarest Oscary energies so extreme that no particle accelerator humans have ever built, could match them. 10 billion electron volts. Where do they come from? What engine in the cosmos accelerates them to such impossible speeds? We don't know. And that mystery, that gap in our understanding, reminds us how much of the universe still operates in silence, just beyond our reach. Symmetry breaking. In the first fraction of a second after the Big Bang, the universe was so hot that nothing we know existed. No atoms, no light, no difference between the forces that shape reality. Imagine a perfect, unbroken mirror of everything reflected into everything else. The strong force, electromagnetism, gravity were all one single unified interaction. One rule governing all existence. But as the universe expanded, it cooled. And as it cooled, something strange happened. That perfect mirror cracked. The unified force shattered into pieces. We call this symmetry breaking. When a force breaks apart into separate forces, the rules of physics change. Think of it like this. Imagine a perfectly round ball sitting at the top of a hill. In that moment, it's completely symmetriferous. No preference for rolling left or right, but the tiniest tremor and the ball rolls down one side. The symmetry is broken. Now there's a difference between left and right. What was undifferentiated becomes distinct. In the early universe, this happened over and over again. First, at temperatures above 1 quadrillion Kelvin, the strong nuclear force separated from what we call the electroweak force. Later, as things cooled further, electromagnetism and the weak force broke apart into two different interactions. Each breaking was precise. Each one changed how particles behaved, how they interacted, what combinations were even possible. Had any of these breakings happened slightly differently, if the timing was off, if the separation wasn't clear, the universe would have been sterile. No atoms, no chemistry, no stars or planets or life. We exist because of cracks that formed in perfect symmetry. We exist because things fell apart in exactly the right way. What does that mean about the universe's memory of unity? The Standard Model. Here's something wild. Physicists have actually catalogued the fundamental pieces that everything is made of. Not just atoms or molecules, we're talking about the deepest level we can see. They call it the Standard Model, and it's like a periodic table for the universe itself. Imagine you break down matter into smaller and smaller pieces. You get atoms, then electrons, then you hit this wall, these particles that don't break into anything simpler. Physicists found 17 of them. 6 quarks with names like up and down, strange, and charm. 6 leptons, including the electron you've heard of. Then photons, which are light itself. Gluons holding nuclei together. W and Z bosons carrying the weak force. And the Higgs boson, the one that was so hard to find they built a machine 17 miles around just to catch it. These particles aren't just floating around alone. They talk to each other through 4 fundamental forces. Electromagnetism glues atoms together. The strong force binds quarks inside nuclei. The weak force makes radioactive decay happen. And then there's gravity, which physicists still haven't figured out how to fit into this framework. Here's what's stunning. This model predicts reality with precision better than 1 part in a billion. It's our most successful theory ever made, and yet it doesn't explain dark matter or dark energy. It can't tell us why particles weigh what they weigh. It's magnificent and incomplete all at once, like we're seeing the pattern clearly, but the blueprint itself remains hidden. Fine-tuning. Imagine you're standing in front of a cosmic dial. On that dial are numbers, the strength of gravity, the strength of the force that holds atoms together, the mass of electrons, the speed of light. These are the fundamental constants of nature. They are what they are, and we still don't know why. But here's the strange part. If you turned that dial even slightly in either direction, the universe would be dead. Let's start with gravity. Gravity is actually the weakest force in nature. Incredibly weak. But if gravity were just 1% stronger, something terrifying would happen. Stars would burn out in a fraction of the time they actually do. Worse, they'd collapse into black holes long before they could forge the heavy elements needed for planets and life. A universe 1% heavier would be a universe of nothing but collapsed remnants. Now, dial it the other way. 1% weaker gravity, and stars never ignite at all. You get a cosmos of cold, drifting matter. No fusion, no light, no chemistry. Then there's the strong nuclear force, the glue holding protons and neutrons together inside atoms. If it were just 2% weaker, protons would simply decay. Atoms wouldn't exist. If it were 5% stronger, heavy elements would never form. Too unstable. The periodic table itself vanishes. There are dozens of these constants. The fine structure, constant controls how atoms interact with light. The cosmological constant shapes how space itself expands. Change any of them by a few percent, and you don't get a different universe. You get a sterile, chemistry-free void. We don't understand why these numbers are what they are. They appear to be cosmic accidents, yet they're tuned with the precision of a master craftsman. So precise that physicists call it the fine-tuning problem. The question that keeps you awake. Why? Why does a universe that didn't need life contain the exact constants required for life to exist? The anthropic principle. So here's a question that keeps physicists awake. Why does the universe look so perfectly arranged for us? The strength of gravity, the mass of electrons, the way light bends around massive objects, the precise energy that fills empty space, the ratio of matter to antimatter of it sits in this incredibly narrow window, where stars can form, planets can cool, and life can emerge. If gravity were even slightly stronger, everything would collapse. Slightly weaker, and nothing would hold together. How did we get so lucky? Here's where it gets interesting. One answer is almost too simple to be true. We observe a universe suitable for life because that's the only kind of universe we could possibly be in to observe anything at all. Think of it this way. Imagine a lottery with trillions of tickets and only one wins. You're surprised you won. But of course, you won. You're the person holding the winning ticket. You couldn't be holding a losing ticket and still be here feeling confused about it. Your existence is proof that something worked out. That's the weak anthropic principle. Our presence in this universe isn't mysterious. It's selection. We couldn't find ourselves anywhere except in a universe that permits observers. But this raises something harder. If we're just one lottery winner among trillions of losing tickets, where are all the losing tickets? What is selecting? What if there are countless other universes, each with different constants, different rules, and we simply happen to exist in one of the infinitesimally rare ones where the numbers came up right? The multiverse. Imagine a cosmic lottery with infinite tickets. On each ticket, a universe. One ticket has gravity twice as strong as ours. Another has it half as strong. On some tickets, light moves faster. On others, slower. Some tickets have universes where electrons never formed. Some where stars burned out in seconds. Some where atoms never clumped together at all. And then there's our ticket, drawn from this infinite pile, with physical laws and constants precisely arranged so that stars could form, planets could cool, chemistry could happen, and eventually you could exist to wonder about it. Most people assume the universe is singular, unique, the only one that exists. But several serious scientific theories suggest something stranger. Maybe infinite universes actually exist right now, branching in ways we cannot see. Maybe they spawn continuously from quantum foam at the edge of expanding space. Maybe they sit stacked beside ours, each one unfolding according to slightly different rules. The first mechanism is eternal inflation. Imagine space expanding not smoothly everywhere, but unevenly. In some regions, expansion slows down and universes crystallize. In others, it never stops. Those regions keep inflating, spawning new universes inside them, which spawn more. This process never ends. Universes are created constantly, each with subtle variations in their physical laws. A second mechanism comes from quantum mechanics. Every time a particle could go one way or another, both happen. Each outcome branches into a separate reality. You measure an electron's spin, and the universe splits. One version of you sees spin up, another sees spin down. Both branches are real. Both branches persist. A third comes from string theory. The mathematics suggests 10 to the power of 500 possible universes could exist, each with different constants. 500 zeros. 500. Each one viable. Each one real. We simply happen to inhabit one where life is possible. Not because we're special. Because we can only exist to ask the question in universes where existence is possible. Tonight, consider this. If infinite universes exist, then infinite versions of you are making infinitely different choices, leading infinitely different lives. Somewhere, you made the opposite decision. Somewhere, you never heard these words at all. And all of them are happening now. Infinite copies. Right now, in this moment, you are made of approximately 7, followed by 27 zeros atoms. 7 sextillion. Each atom arranged in a precise configuration. This exact pattern of carbon and hydrogen and oxygen and calcium and iron, all locked together in one particular way. That arrangement is you. Now imagine space is infinite. Not just really big. Infinite. Endless in every direction. Space so vast that it contains more cubic miles than there are atoms in you. What does that mean for your particular atomic arrangement? It means somewhere else in the cosmos, those same 7 sextillion atoms must fall into exactly the same pattern again. The same cells firing the same way. The same memories encoded in the same synapses. The same you, in another place, having this same thought. Listening to this same voice right now. And not just once, but again and again. Infinitely many times, scattered across cosmic distances so immense your mind cannot hold them. There is a copy of you who took a different job. A copy who said yes instead of no. A copy who died last Tuesday. A copy who became a surgeon. A copy living a life so different from yours that if you met, you might be strangers. But here is where it becomes strange in a different way. If the multiverse exists, then in other universes, with slightly different physical laws, there are yous made of different atoms. Modified yous. Evolved yous. Yous. Shaped by slightly different gravity or different fine structure constants. The question becomes not whether you exist elsewhere, but which version of you is the real one. Which copy gets to call itself original. You are not unique. You are one of infinite variations on a theme. And somewhere far away, another, you, is wondering the same thing. Boltzmann brains. Here is something that will keep you awake, even as you drift towards sleep. Imagine the universe is truly infinite and eternal. No edges, no end. Just endless expansion and endless time stretching into a future so distant that numbers fail us. Now imagine that inside this infinite void, quantum fluctuations to random disturbances in the fabric of nothing air constantly happening. Particles blinking in and out of existence. Energy wiggling where there should be only silence. Here is the unsettling part. Given infinite space and infinite time, even the rarest events become not just possible but inevitable. Even common. Think of it like this. Imagine you have an infinite deck of cards and infinite time to shuffle it. Eventually, you will shuffle a sequence so specific, so improbable, that it spells out your entire life in suits and numbers. Not once. Infinitely many times. Now apply this to atoms. In an infinite universe with infinite time, quantum fluctuations could randomly assemble atoms into the precise arrangement of a conscious brain. A brain complete with neurons firing, memories encoded, the electrical hum of awareness blinking into existence. This is called a Boltzmann brain, named after Ludwig Boltzmann, a physicist who first thought about these kinds of things. But here is where it gets strange. This random brain would exist for only a moment before the heat and chaos around it tore it apart. Yet in that moment, it would experience something. It would feel like thinking. It would carry false memories, visions of a life that never existed, a childhood that never happened, people who were never real. And if the universe is truly infinite and eternal, most conscious experiences would not be like yours. Most would be these fleeting Boltzmann brains, blinking once into awareness, then gone. Which means the probability that you are not one right now, that you are a real mind in a real world, rather than a quantum dream dissolving into nothing, becomes almost impossibly small. Sit with that for a moment. What makes you certain you are not one? The simulation hypothesis. Imagine a civilization so far ahead of us that they make video games look ancient. Not crude games with blocky pixels, but complete universes. Universes where stars actually burn, where planets form and cool, where conscious beings evolve and wonder about their own existence. Universes so detailed, so physically accurate, that the inhabitants have no way to tell they're not real. Now here's the strange part. If a civilization can build one such universe, they can probably build thousands, maybe millions. A rich civilization might create entire libraries of simulated worlds, running simultaneously on computers we couldn't even imagine. Some simulations might be paused. Some might be running at different speeds. Some might be deleted when they're no longer interesting. So think about the mathematics. If one base reality creates 1 million simulations, then suddenly there are 1 million universes in existence, but only one of them is the original. That means statistically, you're far more likely to find yourself in a simulation than in the base universe that started everything. This idea comes from a philosopher named Nick Bostrom. He wasn't claiming we definitely live in a simulation. He was pointing out something weirder, something that doesn't require magic or supernatural forces. It only requires that advanced technology exists somewhere and that simulated worlds are possible. Given those two assumptions, the odds tilt heavily toward us being the copy, not the original. Can we test this? Not really. The beings who created our simulation would probably design it so we couldn't escape or prove its existence. We're not trapped because of the laws of physics. We're trapped because we lack the vocabulary to ask the right questions. So tonight, as you drift toward sleep, sit with this gentle uncertainty. What would change if you lived in a simulation? And more importantly, would you know? Many worlds. So here's where things get really strange. In the last chapter, we talked about quantum uncertainty, how particles don't have definite properties until we measure them. But there's something we haven't asked yet. What actually happens at that moment of measurement? What makes the quantum world snap into a single reality? The standard story says the wave function collapses. All those possibilities vanish except one. But in 1956, a physicist named Hugh Everett proposed something wild. What if nothing collapses? What if the universe simply branches? Think about it this way. Imagine you're flipping a coin, but this isn't just any coin. This is a quantum coin that exists in both heads and tails at once until you look at it. The moment you peek, Everett said, you don't force it to pick a side. Instead, reality splits. In one branch of the universe, you see heads. In another branch, equally real, equally solid, you see tails. Both happened. Both are happening right now. And here's the unsettling part. This isn't just true for coins. Every quantum event, every atom that could decay or not decay, every particle that could spin up or down triggers a branching. The universe is constantly splitting into new versions of itself at the quantum level, billions of times per second, which means there are countless versions of you, in countless branches, living out slightly different lives. In one branch, you chose coffee this morning. In another, you chose tea. In another, you didn't wake up at all. You only experience one branch, the one you're currently conscious in. But the others are out there, just as real as the one you're living through right now. So the question becomes, if infinite versions of you exist in infinite branches, what does it mean to be you at all? Eternal inflation. Imagine you're watching a pot of water boil. Bubbles form on the bottom, rise to the surface, and pop. But what if those bubbles never actually reached the surface? What if each bubble, as it rose, spawned smaller bubbles inside it, which spawned even smaller ones, infinitely forever? That's eternal inflation. And it might be happening right now, all around us, in regions of space we'll never see. Back in the 1980s, physicist Alan Guth noticed something puzzling. The universe appeared remarkably flat and uniform. Why? Inflation theory offered an answer. In the earliest fraction of a second after the Big Bang, the universe underwent explosive expansion driven by quantum energy. This inflation stretched everything smooth and flat, like pulling taffy. But here's where it gets strange. Inflation doesn't stop everywhere at once. Instead, it ends in some regions through quantum tunneling. Imagine a ball rolling down a hill and suddenly appearing on the other side of a barrier. Where inflation stops, pocket universes form. Our universe might be one such pocket. But here's the stranger part. In other regions, inflation never stops. It continues forever, eternally inflating, eternally spawning new pocket universes. These new universes then inflate and spawn their own universes. An infinite cascade, a branching tree of universes, each potentially with different physics, different constants, different possibilities. We exist in one bubble among infinite others. The parent inflation, the original exponential expansion, never truly ends. It just keeps budding off new realities, pocket after pocket, forever. You're not in the only universe. You might be in an infinite ocean of them. String theory. Here's something that might keep you awake in the best way possible. Everything you've ever touched, seen, or felt is made of particles, electrons, photons, quarks. For decades, physicists treated these as tiny dots, dimensionless points with no size at all. But when they tried to do the math, something broke. The equations gave infinity, meaningless answers, contradictions everywhere. What if the problem wasn't the physics, but the assumption? What if particles aren't points at all? In the 1980s, physicists proposed something wild. What if the fundamental building blocks of reality are one-dimensional strings? Not like guitar strings, infinitely smaller. We're talking about 10 to the negative 35 meters. That's the Planck length. So unbelievably tiny that you could fit more Planck lengths across an atom than there are atoms in the observable universe. Now here's where it gets strange. These strings don't just sit there. They vibrate. And depending on how a string vibrates, the pattern, the frequency, the mode, it becomes a different particle. One vibration pattern and you get an electron. A different pattern, a photon. Another pattern, a quark. It's like a cosmic harp where each note is a particle. The theory is beautiful. It naturally includes gravity. It unifies everything physicists have struggled to connect for a century. But there's a catch. For the math to work, for the equations to not collapse into contradiction, the theory requires 11 dimensions. 11. Not 3 or 411. Most of them would be curled up so tightly we could never detect them. We still don't know if string theory is right. We might never know. But it reminds us something important. The deeper you look at reality, the stranger it becomes. Extra dimensions. You live in 3 dimensions, left and right, forward and back, up and down. Your whole life, every movement you make, happens in this three-dimensional space. But what if there were more dimensions hiding in the fabric of reality itself? What if space had 4 spatial dimensions, or 5, or 10, and you simply cannot perceive them? Imagine a creature living on a flat piece of paper, a flatlander. It can move left, right, forward, backward. But height, that third dimension, doesn't exist in its world. Now, imagine you, a three-dimensional being, pushing a sphere through that paper. What would the flatlander see? A point appears out of nowhere. The point grows into a circle. The circle expands, peaks at its widest, then shrinks back to a point and vanishes. The creature would be utterly confused. It could never understand that all of this was just one sphere passing through its two-dimensional plane. The dimension it couldn't perceive explained everything it was witnessing. Now, imagine you're the flatlander, and space has a 4th spatial dimension we cannot see. What would it look like? What would pass through our reality that we'd be unable to understand? String theory, a framework physicists use to explain how the universe works, suggests these extra dimensions actually exist. But they're not hiding somewhere far away. They're everywhere, right here, curled up so tightly at scales trillions of times smaller than an atom that no instrument we've built can detect them. These dimensions fold in on themselves in intricate shapes called Calabi-Yau manifolds. They're so compact, so impossibly small, that they might as well be invisible to us forever. And yet, they might be essential. Everything in the universe might depend on them. The question sits with you in the darkness. What else is here, touching you right now, that you'll never be able to see? Time crystals. Imagine a crystal sitting on your table. Light bounces off it in patterns because atoms line up in neat rows and columns and layers. Space repeats. The crystal looks the same if you shift it one atom to the left. That's spatial order. Now imagine something stranger. Imagine the crystal oscillating between 2 different configurations, back and forth, forever. It swings from one state to another, then back again, in a perfect rhythm. And here's the part that breaks your intuition. It does this without any energy pushing it. It just keeps moving, cycling through time, as if time itself became an axis of structure, the way space is in a normal crystal. This is a time crystal. For decades, physicists thought it was impossible. Frank Wilczek predicted them in 2012 anyway. Then, in 2021, scientists actually built one. They cooled atoms to near absolute zero and arranged them in a magnetic field so precisely that the whole system began to oscillate in sync, returning to identical states at regular intervals. The oscillation never dampened, never stopped, never needed a battery. It violated nothing about energy conservation. Instead, it revealed something deeper. Time and space might be more alike than we ever suspected. In a regular crystal, the pattern repeats across distance. In a time crystal, the pattern repeats across duration. Time became another direction where order could crystallize. Your body changes moment to moment. Your thoughts shift. Everything in nature decays and flows forward. But here in the quantum realm, at the edge of absolute cold, time became still enough to hold a shape. The hard problem of consciousness. Here's a question that might keep you awake tonight, even as you're trying to drift off. Your brain is made of atoms, billions of them, organized into neurons, connected by synapses, firing electrical signals back and forth in patterns we can now measure with incredible precision. We can put someone in a scanner and watch their brain light up when they see the color red. We can trace the exact pathway that signal takes through their visual cortex. We can even predict their behavior by looking at which neurons are active. And yet, there remains something that science cannot explain. Why does seeing red feel like something? Why isn't it just information being processed in the dark, like a computer running calculations in a room with no one inside to experience it? When you taste coffee, the molecules bind to receptors on your tongue. Signals travel to your brain. Neurons fire in a specific pattern. But somewhere in that process, something extraordinary happens. There is coffeeness, a subjective, private, inner experience that belongs only to you. Philosophers call this a quale, the redness of red, the bitter warmth of coffee, the ache of loneliness. Your brain processes the same information a philosophical zombie would, a being identical to you in every physical way. But the zombie feels nothing. You feel everything, and science cannot yet say why. This is the hard problem of consciousness, not how the brain works. That's the easy problem. We're making real progress there. The hard problem is why work feels like anything at all. Why there is something it is like to be you. Some think consciousness is fundamental, like gravity, woven into the fabric of reality itself. Others believe it will eventually reduce to physics we haven't discovered yet. Others suggest it's an elaborate illusion your brain creates. The truth is, we don't know. Your subjective experience, the felt sense of being alive, remains one of the deepest mysteries in existence. Cosmic perspective. Step outside tonight and look up. What you're really seeing when you do that is time itself, light that has traveled across years and centuries to reach your eyes. That star there, the one that catches your attention, the light left before your great-grandparents were even born. It traveled through the vacuum at the fastest speed anything can move, and it still took decades to get here. Now think about galaxies. The light from some of those distant smudges of brightness left before humans walked on Earth. Before we even existed as a species, those photons were already on their journey toward you. Our sun will burn for another 5 billion years. That sounds impossibly long until you remember it's already halfway through its life. Earth will probably be habitable for another 2 billion years after that. And humans, well, we've been here for a few 100,000. You personally, you're here for maybe 80 or 90 years if you're lucky. In cosmic time, that's not even a breath. It's not even the pause between breaths. You're a flicker in the dark, a moment where the universe became aware of itself through your eyes. And here's the strange part that doesn't make your life smaller. It makes it rarer. It makes this moment, right now, listening to these words, infinitely precious, because it will never happen again exactly this way. Your worries don't matter to the stars, but your joy does. It matters because you matter. Not because the universe needs you, simply because you exist. Why there is something. We've traveled through the cosmos tonight, through black holes and quantum foam, through the heat death of time itself, through galaxies we'll never see and particles that barely exist. But there's one question that sits underneath everything we've talked about, heavier than any star, deeper than any void. Why is there something at all? Nothing is easy. Nothing requires no explanation. Nothing needs no reason. A universe of nothing, pure emptiness, no atoms, no light, no time, no space, not even the possibility of anything that needs nothing. It just is. Or rather, it just isn't. And that would be fine. But we're here. There's something. There's you, listening in the dark. There's the world, turning through space. There's light and matter and time folding itself into the shapes we call reality. Why? You can ask why the Big Bang happened. But then you ask why those physical laws existed to allow the Big Bang. And why those laws? And why does the universe follow laws at all? Each answer opens another door, and behind that door is another question, and another, stepping backward into infinity. Some physicists suggest the universe could have borrowed itself into existence that quantum mechanics allows something to pop from nothing, as long as it pays back the energy before the universe collapses. Others say time itself only emerged from quantum rules, so asking what came before the Big Bang is like asking what's north of the North Pole. But maybe there's no door behind the door. Maybe the universe simply is. A brute fact, a basic truth that needs no further why behind it. Something that just is, and we're made of it, aware of it, puzzling over it. And that might be the strangest truth of all. We may never know why anything exists. We may only be conscious enough to wonder. Coda. It's late. The house is quiet. And somewhere in the universe, atoms that were forged in the heart of dying stars, billions of years ago, have arranged themselves into something impossible. Into a brain. Into consciousness. Into you. Think about that for a moment. Those carbon atoms in your fingers, the calcium in your spine, the iron in your blood, all of it was created inside a star. A real star that lived and burned and eventually exploded, scattering its guts across space. And through billions of years of cosmic wandering, through the formation of solar systems and planets, those atoms found their way here, into your body, into this moment where you are awake and thinking and aware. The universe spent 14 billion years building you. Not because it needed you, not because the cosmos required consciousness to exist, but somehow, through pure physics, through the dance of atoms and energy and time, it created something that can wonder about itself. Everything we've drifted through tonight, black holes where time dissolves, the quantum foam blinking in and out of nothing, the infinite copies of you scattered across infinite space, all of it lives in your mind right now. You are holding the strangeness of reality in your awareness. You are the universe knowing itself. That's what you are. Not separate from the cosmos, not a visitor in it, but the cosmos becoming conscious, turning to look at itself through your eyes. And maybe the deepest mystery isn't why anything exists. Maybe it's why consciousness exists at all. Why, in a universe that could have been empty, sterile, silent, something woke up. Something like you. So tomorrow, when the world feels ordinary again, remember this. You are made of stardust, aware of stardust, wondering why stardust wonders. That's enough. That's everything.